We can use the selection operator to create a four-way mux. The four-way mux or the four-way multiplexer looks like this. Instead of selecting 1 out of 2, which is what we did for the two-way multiplexer, we now select 1 out of 4. So we have 4 inputs, and let's denote the inputs as A, B, C, and D. Our selection input is now a 2-bit value. So we need 2 bits to select 1 of 4. And if the select input is 0, 0, we'll select A. If it's 0, 1, we'll select B, and so on. And in this case, we'll denote the output using Y. So this is what our four-way mux looks like. We'll pick 8 as the number of bits for the inputs in this example. Therefore, the output will also be 8 bits. We'll define our output Y as an 8-bit vector of type wire. So using the selection operator, we can create the following continuous assignment statement. We note that our select input is a 2-bit value. In order to make a selection, we need to compare that 2-bit value with 0, 0, 0, 1, 1, 0, and 1, 1. So we start with the comparison to 0, 0. This expression is deemed to be true if select is equal to 0, 0. Otherwise, it's false. And if this is true, we want our output to be equal to A. If our expression is false, we then have to examine the other possibilities. This is the first expression to our conditional operator. This is the second, and we now need to establish the third. So what follows the colon is our third expression. So let's establish that third expression on a new line. We now check to see if select is equal to 0, 1. And if it is, we'll select B. And if it's not, we now need to establish the third expression for this second conditional operator. So the way to look at this is that what we have in this box represents the third expression for our first conditional operator. And then we can continue in a similar manner in here. We now have a second conditional operator with this expression, and we need to establish a third expression for our second conditional operator. And that will be inside this inner box. So let's do that. Select is compared with 2-B 1, 0. And if that's true, the output is C. If not, we then have the third expression for this third selection operator. And that goes as follows. Select is equal to 2-B 1, 1. So if select is equal to 1, 1, we output D. We've nothing left to do, but a good practice is to output all x's for this third expression. So we've got 8-B x, 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 underscore, x, 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 semicolon. So this semicolon is the end for our assign statement. Each box here represents the third expression in a conditional operator. And this is how we normally format the code for a four-way multiplexer. And looking at it this way, it's straightforward to see what's happening. That if select is equal to 0, 0, we output A. If not, check to see if select is equal to 0, 1, we output B, and so on. And in the last case, when we check to see if select is equal to 1, 1, if it is, we output D. And if it's not, it means that select does not match any one of our 4 values. So select does not match 0, 0, 0, 1, 1, 0, or 1, 1, and therefore we output all X's. So this is good from a debugging perspective. In real hardware, we have no such thing as an X value, but for the purpose of simulation and testing, having this possibility handled is a good way to detect invalid values for select. Taking another example, this time a 3-to-8 line decoder. The 3-to-8 line decoder is a combinational logic block that takes 3 input bits and has 8 outputs. It's often used in address decoding for memories. This is the truth table for the 3-to-8 line decoder. And for any given input value, the output contains 7 zeros and a single 1. For example, in the case of 011 for the input, which is the decimal value 3, we note that the 1 in the output is in bit position 3. The bit positions in the output start at bit position 0, then we have bit position 1, bit position 2, and so on. And the way in which the 3-to-8 line decoder works is that for a given input value, the output contains a 1 in that bit position. Another example, if we take the case of the input value being 110, which is the value 6, the output has a 1 in bit position 6. So we only ever have one bit of the output set to 1 and the remaining bits are 0. The dots here and here indicate the LSB. So for the case of 011 on the input, we've got these bits on the output. This form of output is often called a one-hot output. This means that one and only one output is high at a time. For the 3-to-8 line decoder, even though we have 8 bits in the output, we only ever have one of those bits set high. Here is a Verilog module that models the 3-to-8 line decoder, and we make use of the conditional operator for this purpose. We first check to see if A is equal to 000. If that's true, we output these 8 bits. If not, the next check determines if A is equal to 001. If it's true, this is our output, and so on. So we can model our 3-to-8 line decoder in this manner. As noted previously, it's useful for the purpose of debugging and testing to include the case of all X's, which can only occur if A is not one of these 8 values. So in other words, if A contains some X or Z bits, our output will be all X's. It's interesting to note that we could actually code this in another way, which is equally valid, using the logical left shift operator. This is possible because when we look at our truth table, you can see a distinctive pattern in that the 1 moves left to right as we move down through the table. So you can see that as we go from one line to the next, we effectively have a shift to the left. So for example, if A has the value 110, which represents 6 in decimal, we're shifting this 8-bit value to the left 6 places, and the logical shift inserts zeros as we shift left. So the result in this case will be 0, 1, and we fill the 6 vacant positions with zeros. One additional point regarding the shift operators is that in the event that A contains any X or Z bits, the 8-bit shift value will contain all X's. So for example, if we had 0, 1, X for A, the output will be all X's. So while we can use the selection operator for the purpose of modeling the 3-to-8 line decoder, we can also use the logical left shift to model the same functionality, and both are equally useful.